So we were going through MPLS, right? And today we are going to start LDP. Yeah, door close, please. Right? So as I told you before that EICRP, OSPF and RAPE all these routing protocols are just used to exchange routes information among routers, right? Whereas this LDP will be used to exchange label binding. It will be used to exchange label binding, because as I told you that labels have locally significant, but at least they have to tell their neighbors that okay, this is the prefix and this is the label that I am using for it, right? So basically for that purpose here we are having this LDP. Now LDP is a label distribution protocol, which is a reliable protocol actually. I would say not completely, because like in LDP, hello messages will be using UDP itself. In LDP, hello messages will be using UDP, and UDP port number would be 646, right? Rest information will be forwarded over TCP. So basically LDP will be using TCP and UDP both at transport layer, right? And port number will remain same whether it is using TCP or UDP. To discover a neighbor, it will send hello messages, right? Hello interval is by default 5 seconds, and I think its hold down interval is by default 15 seconds, right? So only hello messages will be forwarded with using UDP, and rest information will be forwarded over TCP only, right? Like label binding and everything. And I will show you that okay, this is the information which is going with the help of UDP, and this information is going with the help of TCP. We will capture packets. So finally, you must remember this port number 646, because sometimes in troubleshooting they can block this port number so that your LDP pairing will not come up, and if your LDP pairing doesn't come up, then MPLS will never work out, right? So it can be one of the cause so that your MPLS will not work. TDP is also there, as I told you. That tag distribution protocol is an older Cisco proprietary protocol that has the same functionality as LDP. Although the remainder of this lesson will focus only on LDP, it should be noted that TDP as the procedure of LDP works in a similar fashion. So basically we don't need to go for TDP, we just need to go for LDP only, because TDP is a Cisco proprietary protocol. However, it is having similar function as LDP. So LDP periodically sends hello messages, and every 5 seconds if the label switch router LSR is adjacent or one hop from its neighbor, the LSR sends out LDP link hello messages to all the routers on the subnet as UDP packets with a multicast destination, right? Remember that LDP can send multicast hellos as well as unicast hello. It will be depending on the condition. If you have configured your LDP peer indirectly, I mean, like for an example, your LDP peer is not adjacent peer, it's a non-adjacent peer, same as like in BGP we were having directly connected neighbors and indirectly connected neighbors. So in LDP as well, you can have directly connected neighbors as well as indirectly connected neighbors. So if you are having indirectly connected neighbors in LDP, which means that you have to define your neighbors statically, right? And if you are defining your neighbors statically, then it will be sending its hello messages as unicast messages, right? But in case if your neighbor is directly connected, then it will send multicast hello, right? So TDP will use the TCP port number 711, right? And TDP will also use TCP and UDP both, and port number will be 711. Enabling LSR enabled for LDP will respond by opening a TCP session with the same destination port number 646, and two routers begin to establish an LDP session through unicast TCP. Remember, whatever will be forwarded with using TCP, it will always be unicast, because TCP never works on multicast. You must remember that TCP will never work on multicast, never ever. So once they will agree that okay, they are eligible to form LDP peering, then they will start using TCP, and all the packets in TCP will be unicasted. This is your LDP hello message. IP header will be there. In source it will be a unicast address, destination will be multicast address, then UDP header will be there, source port number can be anything, any random port number, destination port number will be 646, and there will be a transport address as well along with LDP ID. By default your transport address and LDP ID will be same. As you can see here, transport address is 1.0.0.1 and LDP ID is 1.0.0 and colon 0, right? However, it is having some more information in it. But the point is, here transport address is really crucial in LDP, because in LDP transport address must always be reachable, and by default it will be your LDP ID. Whatever you will configure your LDP router ID, it will be your transport address, and in LDP transport address must be reachable. That is why in LDP your router ID must be reachable. It is not like OSPF and BGP. You could define anything as router ID. In LDP you cannot define anything as router ID. You have to define that IP address as LDP ID, as LDP router ID, which you allocated to any interface of that device, of that router. If that IP address is not assigned to any interface of the device, then you cannot allocate that IP to that IP as a router ID to your LDP. So remember that in LDP it is mandatory that your router ID must be reachable. Remember that if router ID is not reachable of LDP, right, that is also known as LDP ID. So if LDP ID is not reachable, then LDP will never form neighborship. This is primary requirement, and sometimes it happens actually in networks. Like for an example, we are running IGPs in between two routers, right? Like OSPF was running. You created some loopbacks on R1, you created some loopbacks on R2, some loopbacks, right? You advertise some of the loopbacks into OSPF on R1, you advertise some of the loopbacks into OSPF on R2 as well, but not all, right? Now you enabled LDP on both ends, you enabled MPLS on both ends. Now you saw that okay, neighborship is not coming up. Yes, it is possible that neighborship will not come up. However, they will keep on to send hello messages to each other. You know why? It will pick highest loopback interface IP as a router ID, and let's assume that highest loopback was not advertised into OSPF. Then of course they will not be reachable to each other, right? So remember that in LDP it is mandatory that their router IDs must be reachable. So you can see
why it's named as transport address.
I don't know, but it is known as transport address. Remember, TCP session will always formed over the transport address only. That's what I know. Right? So now you can see LDP uses well-known port number 646 with UDP for hello messages. A 6 bytes LDP identifier identifies the router identifies the router and label space, right? So basically this LDP ID is a 6 bytes long ID, in which 4 bytes long is router ID, right? And remaining 2 bytes are used to represent your label space, last 2 bytes, right? The source address used for an LDP session can be set by adding the transport address TLV to the hello messages. Like you can change your source address by changing transport address. You see, the actual hello messages which may optionally contain a transport address type length value to instruct instruct the peer to open the TCP session to the transport address instead of the source address found in the IP. So whatever it will do based on transport address. Means that TCP session will always formed with the help of transport address. Doesn't matter what was the source address of hello packets, right? One more thing that you must remember here in MPLS. Here they are talking about label space. And if you talk about the label space, we have two types over there. One is per platform, another one is per interface. Over there you can see can be either per platform or per interface. You can see here, right? So in case of per platform, the label forwarding information based on an LSR does not contain an incoming interface. They will be having only outgoing interface, right? In case of per platform, and by default it is per platform. Remember, it is by default per platform, and the same label can be used on any interface and is announced to all adjacent LSRs. The label is announced to the adjacent LSR only once and can be used on any link. Per platform label space is less secure than per interface label space. Now I will not discuss anything related to this thing because I haven't gone through about this per interface label space and all. I just configured it per platform and we will also configure it per platform, right? Now point is because here we are using per platform label space. Due to this reason only, if you are having multiple interfaces between two routers, let's say this is router 1 and this is router 2, right? You are having multiple interfaces available, right? But once you will enable MPLS on all interfaces in between R1 and R2. Previously in case of routing protocols, what was happening? That routing protocols were forming neighborship between these two routers with using all available interfaces, right? Again, my point. If you configure OSPF form, OSPF will form three neighborship. I mean, three neighbors will be there, right? But in case of LDP, there will be only one neighbor. There will be only one neighbor. However, you will enable MPLS on all of the interfaces between these two routers, but there will be only one LDP pairing. You know why? Due to transport address. Because transport address will be common for device, for entire device. It will not be based on per interface, right? So remember that if you are enabling MPLS between two devices and if they are having more than one interface, one link between them, but still there will be only one LDP pairing. Fine. LDP, discovering LDP neighbors, right? How do they discover neighbors? This is multi-access network, and in this multi-access network you can see that MPLS router A, router B, router C and router D. Four routers are participating in this multi-access network, right? They are interconnected with the help of a switch, right? Then you enabled MPLS on router A, on router B, on router D, not on router C. You haven't enabled MPLS on router C, right? So you see that MPLS, router A is sending hello messages. It is sending unique, multicast hellos, right? With using multicast address 224.0.2. Similarly, router B is also generating multicast hellos. Similarly, router D is also generating multicast hellos. You understand? An LDP session is established from the router with the higher IP address, right? That is your by default transport ID, or you can say transport address, right? So they will send, in this way, and then TCP session will be formed in between router A, router B, router A, router D, and of course B and D. As you can see that TCP is going over there, right? But router C is not participating in it at all, right? The highest IP address of the all loopback interface on a router is used if no loopback interface are configured on the router. The highest IP address of the configured interface that was operational at LDP startup is used. Same as OSPF, but the only difference is that in OSPF router ID, it is not mandatory that your router ID should be reachable, but in LDP that is mandatory. One more thing. First of all, they will send hellos to each other in every 5 seconds, and hold down interval is by default 15 seconds. Once they will form TCP session, then after they will also start sending keep alive messages in every 60 seconds, same as BGP. Do you remember operation of BGP? Like once, after formation of TCP connection, they were sending keep alives in every 60 seconds. Similarly, in similar fashion, LDP will also send keep alive messages in every 60 seconds. LDP session negotiation is a three-step process. First, they will establish TCP session. Second, they will send initialization message. Then they will send initial keep alive, and keep alive sent in every 60 seconds. Non-adjacent neighbors. You can also configure non-adjacent neighbors in LDP, right? You will require to define your neighbor statically, right? LDP neighbor discovery of non-adjacent neighbors differ from normal discovery only in the addressing of hello packets. Hello packets are unicast IP address, and instead, apart from this, everything will remain same. Because TCP was already running on as a unicast, right? But only hello messages were multicasted in case of adjacent neighbor. But in case of non-adjacent neighbor, it will start sending its hello as unicast message, right? You can also configure your targeted neighbor, which is also called your static neighbor, right? As you saw here that we configured LDP pairing with non-adjacent neighbor, right? Where will you use this thing? Where you want to implement FRR, MPLS FRR, then you might require to configure. Tell me. Of course, LDP pairing between non-adjacent devices, right? Or if you want to configure MPLS NSF or MPLS LDP session protection. For these things, you might require to configure a non-adjacent. LDP pairing with non-adjacent router, right? Otherwise, you will never ever require to configure LDP pairing with the non-adjacent router. And here we are not going to form LDP pairing with the non-adjacent router, right? Fine. This is done now. LDP, we have came to know that how does it really work, right? Now it will show you that how is this gonna to propagate labels information across the network. MPLS introduces a label field that is used for forwarding decision, as I told you before, right? We saw that label was inserted in between layer 2 and layer 3 header, right? And devices were switching your data based on labels. Although labels are locally significant, they have to be advertised to directly reachable peers. One option would be to include this parameter in existing IP routing protocol. The other option is to create a new protocol to exchange labels. The second option has been used because there are too many existing IP routing protocols that would have to be modified to carry labels. That is why LDP came into the picture, right? Otherwise, it would have been possible to use routing protocols to exchange label information as well, right? Along with the routing information, because already we are having routing protocols such as EIGRP, OSPF, and BGP, which are responsible to exchange routes between peers. So we could modify them. They could modify them to carry label information as well. But they were already having a lot of routing protocols, right? So they decided to create a separate protocol to exchange label information, that is called LDP, right? FAC is FAC I have already told you, right? You see, in MPLS terminology, a FAC in MPLS unicast IP routing equals an IP destination network, right? And for one destination network, it will be creating one label. That's why I said that one FAC is equal to one label. Remember, router will always generate a separate label for each prefix. MPLS cannot generate same labels for different prefixes. It will never happen. Now, okay, fine. I'm gonna to tell you the functionality of MPLS once again, right? This is router 1, let's say, and this is what, router 2, and this is what, router 3, and this is what, router 4. Let's say here you are having 12.1.1, and here you are having .2, here you are having 23.1.2, and here you are having 3, 34.1.3, and this is what, .4. Now the point is, okay, and then let's say that this is your lane network, right? And let's say you are running MPLS over here, right? Then R1 created, R1 would be having this route in its local routing table as a directly connected, right? And let's say that R1 generated one label for it, right? And that label was 10 for this prefix. Now it will be giving this update to R2, right? That if you wanna, this R2 is gonna to create LFIB, right? All routers will be having LFIB and FIB as well, right? FIB, LFIB, FIB, LFIB, then FIB, LFIB, then FIB and LFIB, right? And let's say that there is a user, right? Fine. Now this router 1 will be having this route will be having this route in its FIB itself, right? Of course it will be having that, but not in its LFIB, because it didn't receive any label from its neighbor, right? It is having it as a directly connected, so it will not be having this prefix entry in its own LFIB, right? So it will be giving this information to R2 now, and R2 will be having this information in LFIB, in its LFIB, right? So fine, it will be having that, okay, 10.1.1.0/24 is reachable via 12.1.1 and this is /24, right? So 10.1.0/24 is via 12.1.1, and next hop, okay, and outgoing label is what? Outgoing label is 10, and local label, let's say it generated what, 20. Then it will be giving this information to R3 that if you want to reach 10.1.0/24, right? And you know, this FIB and LFIB will be generated inside the data plane itself, right? Inside the data plane of each device. So it will be saying that, okay, next hop is 23.1.2 and outgoing label is what? 20 this time, and let's say local label is now 30. It will be giving this information to now R4 and will say that, okay, if you want to reach 10.1.0/24, your next hop is going to be 34.1.3 and outgoing label is going to be 30, and let's say it has generated local label as 40. Fine. This PC, does it understand MPLS? Of course no. Now this PC wants to send some traffic towards 10.1.1.1. Right? So this PC wants to send some traffic. It will send this. It will give this packet to this route 4, right? Now I told you that router will receive two types of packet, either labeled or unlabeled. So which packet it is going to receive this time? Unlabeled, because PC doesn't understand MPLS, right? So a PC will generate unlabeled packet. So this time R4 is going to receive unlabeled packet. So in which table it will perform lookup, in FIB or LFIB? FIB. It performed lookup in its FIB. And in FIB also it will get its outgoing label. FIB also contains this information, right? Apart from LFIB. Of course FIB also contains outgoing label. So it will come to know that, okay, I have to send this traffic out, this packet out from this interface towards R3. Next hop is 34.1.3 and outgoing label is what? 30. So it will send this packet by after adding label number 30. Now R3 received this packet. This time it received labeled or unlabeled? Labeled packet. So if it receives a labeled packet, it will perform lookup in its LFIB. And in LFIB, it knows very well that 30 will be swapped with 20. And exit interface is what? I mean, next hop is this, exit interface is this, right? So it will forward this packet out from this interface with the label number 20. So this time R2 received labeled or unlabeled packet? Labeled packet. That is what? 20. So it will perform lookup in its LFIB once again, right? And in LFIB, it will see that okay, 20 is swapped with 10, and outgoing interface is this interface, right? So it will send this packet out from this interface with the label number 10. So this time R1 received labeled or unlabeled? Labeled packet. It will perform lookup in its LFIB. Was it having this entry in its LFIB? No. So if entry was not found in LFIB, then it will perform lookup in its FIB. FIB. Only FIB, right? And then it will come to know that okay, it is directly connected. So this router 1 was required to perform lookup 2 times. First in LFIB and second in FIB. So it is performing now recursive lookup. And this is not really good, because if it is performing lookup twice, then of course its CPU utilization would be higher in case of like if you are transmitting some heavy traffic and all, right? So this is not good. To solve this problem, now we are having a concept over here that is called PHP. That is called PHP, penultimate hop popping. Penultimate hop popping, PHP. To solve this problem, now we are having PHP, penultimate hop popping. Penultimate hop popping. Right now, PHP is by default enabled nowadays in MPLS, right? This feature is by default enabled. And what does it mean? Now just try to understand it now. See, this is router 1. Once again, I'm going to draw same diagram. R3, and this is what? R4. As 0 by 0, 0 by 0, this is 0 by 1, this is 0 by 0, 0 by 1, and this is 0 by 0, right? Fine. This is having 12.1.1.2, 23.1.2, this is .3, 34.1.3, and this is .4. Fine. Now PHP is by default enabled, right? So remember, for directly connected prefixes, it will generate implicit null. Label number, label implicit null. Remember, now after enabling this PHP rule, routers will generate implicit null label for directly connected prefixes. So this time it is not gonna to generate label number 10, right? It will generate implicit null for directly connected, right? For this. So it will be giving this update to R2 now. LDP will be giving this binding to R2. That if you wanna reach 10.1.0/24 via sorry 12.1.1 exit interface, tell me 0 by 0. then outgoing label is going to be now implicit null, which means pop, which means pop. And local label can be anything. Now we'll start from 16. Remember that from label number from 0 to 15 all are reserved, all are reserved. Actually this implicit null is also a label number itself. In numeric form it has a label number, but as alphabetical its name is what? Implicit null. I think it's a label number 1 or 3. I'm a little bit confused. I think yes, it is 3, right? So it's a label number 3. So in actual it is label number 3, but it will show you implicit null. So whenever R2 will receive this prefix with implicit null, so its outgoing label will be pop, right? Although it is having this entry in its LFIB, this entry is inside LFIB itself, right? Then R2 will be giving this information to R3 that if you want to reach 10.1.0 so as 24, you can reach it via 23.1.2. Exit interface is 0 by 0, and outgoing label this time it is going to be 16 because R2 generated 16, right? And the local label is 16. Yes, it can have. It is possible that your outgoing label and local label can be same, because labels will be allocated to your prefixes in a sequence. Let's say I received one prefix, right? I mean R3 received one prefix from its neighbor. It will allocate a label to that prefix now. Whatever will be next available label number will be allocated by R3 to that prefix. So let's say this time the available label number was 16, so it will allocate it as 16, right? So it is not like that that router cannot allocate same label numbers to the prefix, to the prefix, right? As it received label number along with that prefix. So this time R3 received this prefix with the label number 16. It can also generate the same label for this prefix, right? But remember, for two different prefixes it cannot generate same label number. Let's say 10.1.2.0 is also coming onto R3, right? Now R3 cannot allocate the same label number 16 to that different prefix, right? It is not possible. Then R3 will be giving this information to R4 that if you want to reach 10.1.0/24, you can reach it via 34.1.3. Your outgoing label is going to be 16. Local label is again, let's say 16. However, of course, in some cases it can be same, it can be different, right? And this time you see that, let's say once again there is a PC wants to send some traffic towards 10.1.1. This is the destination IP address. It will be received by R4. R4 will receive it without label, unlabeled packet. So it will perform lookup in its FIB. It will come to know that, okay, I need to send it out from this interface with the label number 16. So it will forward this packet with the label number 16 towards R3. Now R3 will receive labeled packet, so that it will perform lookup in its LFIB. So it will perform lookup in its LFIB, and in LFIB 16 is mapped with 16 and outgoing interface is 0 by 0. So it will send, this R3 will send this packet out from 0 by 0 with the label number 16 itself, right? Now this R2 received what? Labeled packet. So because this time R2 received this labeled packet, will perform lookup in its LFIB, and if it performs lookup in its LFIB, again it will see that, okay, 16 is mapped with pop. So what is the meaning by pop? That it has to remove this tag, right? So it performed lookup in LFIB and it came to know that what is the exit interface, right? So it will send this packet out from this interface but without any label, because it has removed that due to this pop. Outgoing label was pop. So this time R1 will receive labeled packet or unlabeled packet? Unlabeled. So directly it will perform lookup in its FIB, not in LFIB. Have you understood it? So with the help of this feature, this rule, they have avoided this that problem of recursive lookup. This is called PHP. So basically labels will be removed before one hop. This procedure is called PHP, penultimate hop popping. right? Theory is done now. That's all about the theory of LDP. In future, of course, we will learn about VRF and all other things, but for now, that's enough. Let's start some practicals of LDP and all. I'm gonna to prove it now. This is R1, R2, R3, and this is what? R4. Understand? This 101 only, right? I'll be having this 101. Along with that, let me create some loopbacks as well on R1, like it is 1111, and on R2 I'll be creating 2.2, and on R3 I'll be creating 333, and then I'll be creating 4.4.4, right? Interface F0 by 0. Is it visible to all?
Yes, sir.
IP address is going to be now 101.1. Now you see, I'm gonna to enable LDP in between R1 and R2, and they are adjacent devices, right? And to enable that, you see that I went on F0 by 0, and I said MPLS. See, to enable it, it is very simple, MPLS IP. That's it. LDP is enabled now. To enable LDP, this is the only command, right? Now see, show MPLS. Sorry, show IP MPLS. So MPLS interfaces, you see, LDP is running on fast Ethernet 0 by 0. Similarly, you can move on R2 F0 by 0 MPLS IP. So MPLS interface, LDP is running, right? Any problem? Yes, there is a problem. Neighborship is not coming up. It does not mean that they are not sending hellos to each other. You see, they are sending hellos to each other in every 5 seconds. Check it out. You can open them, right? See, they are giving hellos to each other. But if you open hello message, transport address, and which is not reachable. Right? So you do one thing now, and see, they are using UDP, user datagram protocol, right? It's not TCP.
So we can't create the LDP membership on physical interface.
Or do one thing, use their physical interface IP as transport ID. Then they can form.
Manually we have to configure that.
And the command I think is MPLS LDP. There is a command actually by which we can change its not router ID actually. That is for router ID. Even there is a command to change transport ID as well. I just forgotten that command, but there is command to change transport ID itself, right? We can change that. But this time I'm gonna to do one thing here. I will just add, I will simply configure, IGP like OSPF or EICRP. So usually, not usually, you will never see EICRP running in the background of MPLS. Never ever. You will find either OSPF or ISIS. Router OSPF1, router ID, network. Here you can allocate any router ID in OSPF, right? And then you can say route 000 to show history. They can pick their router ID automatically, right? So I don't need to define their router IDs in OSPF. But finally they will form neighborship with each other, right? But we have to do wait because this is multi-access network, so they will elect DR and PDR, so it will take some time. Show IP route. It haven't received the loopback of R2 yet. Once it will receive the loopback of R2, you will see that LDP pairing will also come up, right? They are sending now hello messages to each other. Fine, done. And now LDP pairing will also come up. You see, it has came up. This is the LDP session. You see, I'm gonna to stop it. In LDP, they were sending, hellos to each other. Then one of them send SYN message, right? And SYN was generated by 22222. Remember that in LDP, TCP session will be initiated by that device which is having higher IP address. Higher transport ID. So this time you can see 2 have initiated this TCP session, right? It generated a SYN message, and then after SYN plus ACK, and finally ACK, and then after they have given initialization messages to each other, right? And then finally they have started to send keep alive messages to each other, right? And they have also given label binding, some label binding mappings. You see, one is giving it to 2, one is giving it to 2. This label binding, you see, label mapping. Fact, this is fact element 1 for this. This is the label number. Where is the label number? What? Due to implicit null, because 111 is directly connected to R1. Prefix is 111, which is directly connected to R1. And I told you that for directly connected, it will generate implicit null. and in numeric value it will be 3. So R1 is giving this information to R2. So now LDP peering has came up, right, in between R1 and R2. Even you could say router OSPF1 MPLS LDP. That's the best idea to enable LDP in OSPF. You don't even require to enable LDP onto interfaces of your devices. LDP will get enabled on all those interfaces where OSPF is running, but only on physical interfaces, not on loopback interfaces. LDP can be enabled only on physical interfaces. Even you cannot, even explicitly you cannot enable LDP onto loopback interfaces. That's not possible. So that is why if you enables, like this LDP in this manner, like you have to say router OSPF1 and then MPLS LDP, you see auto config, right? And similarly on R3, say router OSPF1 MPLS LDP auto config. In similar fashion, go to R4, say MPLS LDP auto config. This command is not available in EIGRP. This command is enabled, in this manner, in this fashion, you can enable LDP either in OSPF or ISIS. ISIS also has this command, so that LDP will get enabled on all those interfaces where IS will be running, right? So this time you can see on R3, show MPLS show MPLS interfaces. You can see that now LDP has enabled onto these two interfaces, right? So in this manner, you enabled LDP now. Understood? But one more thing over here I would like to tell you, that you enabled MPLS LDP in OSPF itself. Now go to F0/0, say no MPLS, or you say MPLS, or do one thing. And if you want to remove it from here as well, then say MPLS LDP, just configure this command. Now even you have enabled it inside OSPF, but it will not be enabled onto this interface, right? So this is the command that you can use over here. Clear? So now show MPLS interfaces. You can see that LDP is running on F0/0 as well as on F0/1. Fine. To see your LDP neighbors on R1, you see show MPLS LDP neighbor. This is your LDP neighbor. This is your LDP identifier of neighbor. This is your label space. Do you remember? And local LDP identification. This is local LDP ID. TCP connection 222. And this is right, which means that it was initiated by 2222 because it is having random port number, right? And this 114111 we are having well-known port number, right? So now you can see uptime is 4 minutes 39 seconds. Source address is 12.1.2. Of course, we are having neighborship with 12.1.2. However, transport address is quite different, right? And LDP ID could be on remote host. LDP ID could be either 12.1.2, 23.1.2 or 22222, but it picked 22222. It is showing you that these are the addresses which are available to be a LDP ID on neighbor on router 2, right? So these IP addresses are configured on router 2. Then after it, you can also say show MPLS LDP neighbor detail. So here it will show you that for hello messages, hello interval 5000 millisecond, which means 5 seconds, 15,000 millisecond for hold down time, which means 15 seconds, right? That's fine. And for keep hold down interval for TCP, it is 180,000 milliseconds, which means 180 seconds, right? And keep alive interval is 60,000 milliseconds, which means right? And period state is what? Established, which means it is in established state. Any problem? Then after it,
what are the significance of label space?
this one I think that is per platform or per interface only, and that is negotiated between them automatically, that okay, they are using per platform. There is some theory behind it. Then after it, you can also see show MPLS discovery. My god. MPLS LDB discovery, right? Right? Transport address on R1 as well as on R2. Now in case if someone have enabled this command, MPLS label protocol, this is the global configuration command, right? In global configuration mode, you will be running this command. So you have instruct your device to use TDP as a label protocol. So you will see that now neighborship will never come up, never ever. So in troubleshooting, you must be careful. Under interface mode, you can say MPLS label protocol is what? So if you have configured LDP under interface and globally TDP is running, then of course it will pick that protocol which is configured under interface. So now neighborship will come up. And in case if you have configured like MPLS label protocol is what? TDP under interface mode, and globally you said MPLS label protocol is what? LDP. Globally LDP is configured, but under interface TDP is configured, so of course it will pick TDP. So you have to at that moment you will require to change your done. Neighborship has came up once again, right? One more thing that they can do, they can filter all the packets which are coming with the port number 646 with the help of NACL. So you must be very careful with all these things in MPLS, right? After all these things, let me show you that how can we see LFIB and how can we see lib. You know very well that how to see rib and fib. To see rib, it is very simple, show IP route, and to see fib, it is very simple, show IP. Similarly, if you want to see lib, label information base, the command is show MPLS LDP binding. This is your lib. However, here it will show you tib, but it is actually lib. Tib, I think it should be like tag information base, right? If you want to see LFIB, then the command will be show MPLS forwarding table. This is called LFIB. Now, see, I told you that in local LFIB, it will never be having directly connected prefixes. Does it have 101 in LFIB? But in its SAF table, it has. Is not it? Then it will generate, as I told you, that it will always generate labels for all prefixes, right? So it is directly connected, then definitely it will generate one label for this as well, right? So to see that, show MPLS IP binding. So for 1111 implicit null. This is implicit null, right? There is one another command that you can use here. So MPLS LDP bindings. For 111 local binding is what? Means we generated implicit, but we also got one another label for it given by 222. Because you know there is a rule, there is nothing like a split horizon, right? If I am receiving any prefix, I will generate label for them and will give it to all neighbors. So R1 has given this prefix to R2. R2 generated one label for this prefix and R2 has given it to its neighbor R1 as well as R3. Right? So basically R2 generated label number 16 for this prefix. But here we are talking about local binding. Local binding is what? Implicit null. So it will be giving this information to its neighbor R2 now. And R2 will receive it, right, from its neighbor R1. And you can see that. Show MPLS LDP binding. Check it out. For 111. Remote binding given by 111 is what? Implicit null. Local binding is what? 16 and given by 333 because we have also given this prefix to 333. So 333 will also generate one label for this prefix and that generated 16. So MPLS forwarding table. You can see that for 1111 its outgoing label is now what? Pop tag because it received this prefix from 12.1.1 with label implicit null. So now outgoing label has become, tell me, outgoing label is now what? Pop. Outgoing interface is this, next hop is this. Remember in case of multi-access interface, multi-point interface, you will see next hop address, right? But if you are having point-to-point interface like serial interfaces, then you will never get this next hop address. You will be, in place of next hop address, it will be having point-to-point connection. Because in case of point-to-point, you never require to have next hop address, right? Because in case of point-to-point, there will not be any requirement of sending ARP request or something like that, right? So that's the thing. Fine. Then after it, you can see for 101.1 that was also directly connected to R1. You understand? Directly connected to R1. So R1 has given this prefix to R2 with the label number implicit null. So that is also pop tag. Now local label for 111 is 16. For 168.101.0 is what? 17. Now R2 will be giving this information to R1 as well as R3. So let's move on R3. Because R1 is what? I think for it will be downstream and upstream will be R3. It will be giving this label information to its upstream router, right? So upstream is what? R3. So move on R3 now and you see show MPLS forwarding table. For 111 it received outgoing label is what? 16 because for R2 local label was 16. For R2 for this prefix local label was 17. So for R3 it has become now 17. Now they will also generate local label for them. So for 111 it have also generated 16. But for 101 it have generated 20. Now this local label will be outgoing label for R4. You can move on R4 now. Show MPLS forwarding table. So for 111 you see outgoing label is what? 16 and it have also generated label number 16 for this prefix, right? Then for 101 its outgoing label is 20 that was generated by R3 and local label is what? 21 that is generated by Bolo. Done? Any problem? So in this manner they are exchanging their label bindings and I show you we saw that how do they send this mapping, you see, in this manner, right? You can open any binding mapping forwarding equivalence class fact element general TLB. This is prefix 101 and this is what? Label number. 101, right? And that is given by, I think, yes, that is given by 222. Source is 222, right? Because whenever R1 will be giving this binding, then of course its label number must be 3, implicit null, because it is directly connected to R1, right? So this binding was given by 222. You see,
TLV क्या होता है?
क्या
TLV
टाइप लेंथ वैल्यू ऑप्शनल पैरामीटर्स लग करके जाते हैं ना इसमें, चाहे कोई भी TLV, किसी भी प्रोटोकॉल में TLV ले लो। हाँ,
तो इसमें क्या चीज है?
जो भी ऑप्शनल बाद में जो भी ऐड होता है वो TLV में ही जाता है। जैसे BGP में ओपन मैसेज के अंदर भी TLV होता है, तो उसमें कैपेबिलिटीज वगैरह लग करके जा रही होती हैं,
राउट रिक्वेस्ट तो
वो सब TLV में ही जाता है। Right? So in this way it will work. Now how can we prove? See, PHP is there, right? By default PHP is there. That is why now R2 is performing popping for directly connected prefixes of R1, right? So from R4 even you can try it now, trace route 1.1.1. You see that when it reached 12.1.1, at that moment it was not having any label. Mail मेरे को CC में नहीं रखा. You see now that it has reached 34.1.3 with the label number 16, then again 16, and then this is for 111, right? And if you trace route 192.168.101.1, so it is using label number 20, then 17, and then without label, right? So you see, why 20? Show MPLS LDP forwarding, sorry, show MPLS forwarding table. You see, to reach 101 outgoing label is what? That is why it used 20. Then it moved on R3. If it receives anything with label number 20, because it will look up its LFIB only, right? If it receives anything with label number 20, then it will swap it with label number 17. So what is that? On R4, yes, that was 17. Now it would be received by R2. If R2 receives anything with label number 17, that is local label, right? So outgoing label is what? Pop. So finally packet reached R1. That's fine. Fine. So in this way it is working. And now even you can see here that how many packets switched with the help of this, you see, for 101. 672 bytes, right? In similar manner you can try to ping with that from R4. And you see how many bytes were switched, right? Fine. You see, it is going with label number, and label is always inserted in between, in request, not in reply. Remember, label will be in request, not in reply, because if request is going, then only it will add this label, right? Because and if traffic is coming back, then it will be popped by, label will be popped by R3 itself. For returning traffic, R3 will be performing popping. Or before that, actually, even R2 will perform popping because it is directly connected to R3, right? So you see that in between layer 2 and layer 3 you are having MPLS header. This is only one label, 20 bits to represent your label number. So that was 20. 3 bits are for experimental bit. This is 1, which means this is the last label before IP header, right? Then 255 for TTL. When packet moves into MPLS domain from non-MPLS domain, then TTL from IP header will get copied back into TTL of label, MPLS label. Whenever packet will exit from MPLS domain, then again TTL of MPLS label will get copied back into IP header. And if it does not happen, you see, if I disable this propagation, this TTL propagation, this is called TTL propagation, right? And this is by default enabled. If I disabled this propagation, see what will happen now. If I trace route, now trace route 191.168.101.1, right? So it is showing me that okay, it is going through 3, 2, and finally it reached 1, just because of that TTL propagation is enabled, right? But in case if I disabled this TTL propagation, and to disable that command is MPLS IP propagate TTL, right? So say do show history and just configure this command on all devices now. No MPLS IP propagate TTL. Similarly on R1. Fine. And now after you see trace route 191.1.1, it has reached directly destination. You have hidden your core by disabling TTL propagation. It will never ever show you that okay, these are the devices which are in between. And that's what they have configured, I mean, in production environment. I mean, I'm talking about service providers. They will never allow customer to see all the devices in their core. They will be able to see only edge devices, nothing else. So now you can see that from here we are directly moving. We have directly reached destination. However, does not mean that directly, I mean, traffic is going through air. It's not going through R3 and R2. Still traffic is going through R3 and R2, right? But due to TTL, I mean, due to disabling TTL propagation, it is happening now. Right? I hope you have understood it now, right? This TTL propagation. As I told you, when packet gets entered from non-MPLS domain into MPLS domain, TTL value from IP header will get copied back into MPLS label. When packet will exit from MPLS domain, then again TTL value will get copied back from MPLS label into IP header. So previously what was happening, because in trace route you know that it reaches destination hop by hop. First packet with TTL1, second with TTL2, third TTL3, fourth, 5, 6, in that way. But this time you see, I mean, like we were previously we were able to see R3 and R2. You know why? R4 generated very first packet with TTL value 1 in trace route. So it reached R3, but it was dropped by R3 itself. That is why reply came from R3 itself, that it is, you know, unreached. I mean, TTL has expired now. So that is why R4 got reply from R3. Then next time R4 generated packet with TTL value 2. So it expired on R2. So R2 given reply back to R4, right? And then 3, and it was getting copied from IP header to MPLS label. That is why it was dropped on R2. Because R2 and R3, I mean, R3 is R3 is switching your packets based on labels, not based on IP header. And this time, because you have disabled propagation, TTL propagation, which means that your TTL value from IP header will not get copied back to MPLS. Are you getting my point or not? Yes. Your TTL value from IP header will not get copied back to MPLS label. So this time, in very first attempt, when you say trace route, so it will send packet with TTL value 1. It will giving it to R3. But before that, label will be inserted by R4 itself, right? Before sending packet, R4 will insert a label. But in that label, this time it is not copying TTL value from IP header into label TTL value. So in label, TTL value will remain as 255. TTL value will remain as inside label, right? TTL value will remain as 255. That is by default TTL value of label. However, inside IP header, it is still what? 1. But this time when R3 will receive it, it will switch that packet based on label. And in label, TTL was 255. It will forward it towards R2. Then R2 will forward it towards R1. That is why from R4, now you can't see either R3 or R2. Have you understood this function or not? See, remember, by default TTL propagation is enabled, right? What does it mean? That whenever packet will get entered into MPLS domain, MPLS will add a label onto that packet. Whenever it will add a label, then it will copy TTL value from IP header, whatever it was, right, into MPLS label. Fine. By default, it is 1 when you trace route anyone, right? By default, TTL is what? 1. R4 added a label onto that. It copied the TTL value from IP to label now, and it became as 1. R3 received labeled packet. In that labeled packet, it found that TTL value is what? 1. It got expired. It given reply back to R4. So R4 came to know that okay, R3 is there. Fine. Then R4 generated next trace route packet with TTL value 2. Then R4 added another, again R4 added a label in between L2 and L3 header. Fine. And it also copied TTL value from IP header back into MPLS label. This time it was 2 received by R3. R3 will decrement its TTL value by 1. Then it will give that packet to R2. R2 also received a labeled packet with TTL value 1. It got expired. Given reply back to R4. Next R4 next time will generate with TTL value 3. And again R4 will be responsible to add a label. So I hope that you people have understood it now completely, right? And this time because you have disabled propagation, what does it mean? That this time it is not going to copy the TTL value of IP header back into MPLS label. So very first time when this R4 will generate trace route packet, very first packet, it will generate it with TTL value 1. But this time R4, of course R4 will insert MPLS label in between L2 and L3 header, right? But this time it is not gonna to copy TTL value from IP header back into MPLS label. So it will remain as 245. So once now it will reach R3. R3 will receive this labeled packet with TTL value 245. It will give it to R2. R2 will receive labeled packet with TTL value 245, and it will give it back to R1. That's it. It has reached destination. So who will be giving reply now of very first trace route packet? R1 itself. I hope that you have understood this TTL propagation as well, right? Fine. How to change LDP router ID? MPLS LDP. It's very simple. You can call only interfaces. It's not like OSP you can allocate anything. No, you can call only interface. And if you are calling interface, which means that you have allocated any IP to that interface, right? So that is why there is no option to allocate anything as router ID, right? You have to call your interface. And of course, if you are calling an interface, which means that you have allocated an IP address to that interface, right? But make sure that you advertise that interface into your ICP so that it will be reachable from its adjacent device, right? Because TCP neighborship will be formed over transport address only. And see show MPLS, show TCP free. Check it out. 646, right? Right. Apart from that, MPLS LDP. MPLS label range. By default it is right, and to see that, show MPLS label range. It is by default this one, but you can configure it up to, right? So you can change it by using command MPLS label range and then start minimum label value. By default it is 16. I told you that from 0 to 15 it is reserved, and we are using them from 4 different functions. Like 3 is used for implicit null, so 0 will be used for explicit null, and some others are also there. 10, sorry, 100 to, now you see, but changes will take effect after next reload, right? So in this way you can change it. And MPLS you can also do it right, like output label, you can modify it. That's in the next hop, right? So you can statically enter your binding over here. Apart from that, LDP, you can also configure conditional label advertisement. You can also configure conditional label advertisement, right? And you see show MPLS forwarding table. Right now it is receiving either it is having either pop tag or some labels in its outgoing, right? Similarly on R4, show MPLS forwarding table, either pop tag or some outgoing values, right? But in case if you say that from R3 interface F0/1 MPLS label protocol is what? TTP. So neighborship will go down now, right? And now you see show MPLS forwarding table. Outgoing is what? Untagged. If outgoing is, if it is showing you untagged, which means it didn't receive anything from its neighbor, it didn't receive any label for these prefixes, right? That is why it is showing you untagged, which means that whenever it will forward packet for these prefixes out from this interface, it will forward them without any tag. Again it will start receiving. You see neighborship has came up, binding has exchanged between them, and now again it is having some outgoing labels and all these things over here, right? So this is the way to implement LDP in running network. We saw that now core devices are not looking for IPv4 header. They are simply switching your packets based on their labels. Now you would say that how can we prove it that okay it is happening like that? So we can also prove it. You know how? I'm gonna to do one thing. I'll configure out to BGP, right? Okay, let me create one loopback on R4 as well. And previously, do you remember that we were required to configure GRE tunnel in BGP, right? That's fine, right? Now show IP interface brief. I didn't advertise it's 101. I just enabled OSPF only on loopback and pass Ethernet 0/0. Show IP route. You see we are receiving 44444 on R1, and on R4 I must receive 111, not 101, right? So 101 is not there, but 111 is there to form indirect BGP peering, right? So now I'm gonna to do one thing. I'll say router BGP 100, neighbor is 4.4.4, remote AS is let's say 100 itself, 4.4.4, update source is loopback 1. Any problem? And then say network 192.168.101.0. Similarly, I will move on R4. I'll say interface F0/0, sorry, router BGP and 100, neighbor is 1.1.1, remote AS is going to be 100, neighbor 1.1.1, update source is loopback 1, right? And then I would say network, let's say here we are running 104.0. For that I'll create one loopback 10 and I'll allocate this 104.1, and neighborship has came up, right? And now you can see show IP PCP, check it out, that 104 is there, yes. And on R1 show IP PCP, check it out, 101 is there. Let it become best first, and then after they will exchange their routes with each other, they will become best, they will install these prefixes in their routing table, and also they will ping with each other. Wait for a moment, BGP converts slowly. Previously we were required to configure either or redistribution, right? You see it has become best now, right? So IP route BGP. So 104 has been received by R1. Similarly on R4 show IP route, check it out, 101 is there, but still source, you see 0 by, and these routes are not available in the routing table of R2, and of course you can look at there, and packets are going through R2 and R3, although they do not have those prefixes in their routing table, but still traffic is going through it. You know how? Just try to understand it now. We are pinging from R1, just go through the concept, nothing else. 104, it will perform lookup in its FIB. As I told you, if it receives any unlabeled packet, then it will perform lookup in its FIB. So show IP SEF 192.168, 104.0, 255.255.255.0. Check it out. 104 is received from 4.4.4, and to reach 4.4.4 it has to go through fast Ethernet 0 by 0, where MPLS is running, and outgoing label is what? 18. Show MPLS forwarding table. To reach 4.4.4 outgoing label is, so what is it saying, right? So it will forward this packet out from F0 by 0, but after adding label with the label number 18. Understood? Fine. It given this packet to R2. R2 received this packet with the label number. Which means that R2 received labeled packet, right? Which means it will perform lookup in its LFIB, not in its FIB. Because in case if R2 perform lookup in its FIB, it will drop this packet immediately, because it will open IP header. But this time it is not opening its IP header. It will open only MPLS label, and in MPLS label it found label number 18, right? So MPLS forwarding table, you see, if it receives anything with label number 18, this is local label 18. It will swap it with 18 itself. It will swap it with 18 itself, and will forward it out from F0 by 1 towards 23.1.3, which means now packet will be delivered on R3. And R3 again received a labeled packet with the label number 18. So MPLS forwarding table. If it receives anything with the label number 18, then it will perform popping, and it will forward this packet out from F0 by 1 towards 34.1.4. So finally packet delivered on R4, and R4 received it as a unlabeled packet, so it will perform lookup in its FIB, and that is directly connected. That is why packet have delivered onto R4. In similar fashion, packets will come back from R4 to R1, because if R4 is replying back to 101, so 101 is received from 111, right? And if you, because it will look up its SAF table, right? FIB table. So it will say show IP SAF 191.168.101.0. Check it out. To reach 101, it will impose label number 16, because to reach 111 its label number is what? However, there is a recursive lookup. Because to reach 101, next hop is 111. To reach 111, next hop is 34.1.3, and label is 16. Right? So MPLS forwarding table. That's it. To reach 111 is 16. So it will forward it with label number 16. It will receive with 16. If it receives anything with 16, it will forward it out from F0 by 0 with the label number 16 itself. Then R2 will receive it with the label number 16. If it is receiving anything with 16, it will pop tag and will forward it out from F0 by 0, which means that finally packet will be delivered on R2. So with the help of MPLS, we have defined our core network as a BGP free core. See, BGP is not running over there and there is no problem in their communication at all. Understood or not?
IGP is one.
Of course, IGP is formed. That's why we were able to form indirect neighborship for IBGP. Right? I hope you people have got all these points related to MPLS till now, right? Finally, I'll go for now conditional label advertisement, right? By default, routers generates labels for all prefixes and also advertise them towards all neighbors, right? Fine. On R2, to stop default conditional advertisement, we can say MPLS MPLS LDP advertise labels, right? So we can say no MPLS LDP advertise label, which means it is not going to advertise any label. It will generate them but will not advertise them to any peer. So this time you can see that on R1 it's untagged now because it is not receiving any label for any prefix now from its neighbor. And now BGP, you won't be able to ping. You won't be able to. Previously you were pinging, right? It was working fine, but this time you see. So in T-shoot, because this time packet will be forwarded without any tag. And if R2 is receiving anything without tag, which means it will perform lookup in its fib, it will open IP header, right? And route is not available in the routing table of R2. That is why R2 is dropping all these packets. Once you will enable this command, once again, I'm talking about troubleshooting. Once you will configure this command, and now you will see that even if SAF is not running, no IP SAF, because if SAF is not there, LFIB will not formed. LFIB will not formed, and you see. Let's go to R2, say IP, and once again you will see that it will start communicating with destination, right? Then if I wanna say MPLS LDP advertisement labels, you can also advertise labels with some conditions. Like I want to advertise prefix, label towards R1 or towards all for the loopback of R4 and for the loopback of R3 only. So I'll create one access list, 10 permit, and along with that let's say 222 is also there, right? And access list one another ACL20, this is for neighbors, permit any for all neighbors. I will apply it for all neighbors now, right? So I will say MPLS LDP advertise label for which prefixes 10 to all neighbors 20. Let me show you what's the meaning by for. Destination prefixes. For will specify destination prefix. So for prefixes I called ACL 10. Then 2 means LDPPS. For that I created ACL number 20. So this time it is not communicating, but you will see that it will start communicating with that. MPLS forwarding table. Yes, for 4.4.4. Oh, now the point is R2 is not giving any label, so reverse path is not there now. because R2 is not giving label to its peer R3 for 1111. You see, is untagged for 111. So whenever traffic will come back, it will send without any tag towards R2, and R2 will simply drop it for return traffic. That is why you can still receive those ICMP packets over there. Let me show you on R4. Debug IP ICMP. Let me show you. Reply sent, which means it is receiving ICMP echo request. It is giving echo reply, but echo replies are dropped by R2. R3 is giving reply to R2 without any label. That's what they can do actually in troubleshooting. So at that moment, you have to look at the running config of MPLS. You can see that, okay, there is a conditional label advertisement. So in this ACL 10, just add this 111 as well. Show IP access list. Check it out. Say IP access list standard 10 permit 1.1.1. Fine. It will work fine now. So these are very small things, but really tricky to figure out. So it's all about label. It's all about label, nothing else in MPLS. Rules are very simple. Router is receiving labeled packet will perform lookup in LFIB. Router is receiving unlabeled packet will perform lookup in FIB. So if you are doing troubleshooting, keep it in your mind that, okay, whether it is receiving labeled packet or unlabeled packet. Because accordingly your router will behave. SAF is one of the key feature, right? And of course this conditional advertisement as well, LDP peering, everything. Right? So I think that's enough from the side of LDP now. We don't have anything else in LDP now. Understood? This is not VPN actually. I just wanted to show you that, okay, with the help of MPLS we have defined our core as BCP free core, right? But this is not this is not VPN. Later on we will also learn VPN, MPLS VPN, right? Fine, then I think